Welcome to Electromagnetism Part 1. In this video, we're going to take and do a basic introduction to magnetism, and then we're going to get to look at some more things in electromagnetism in later videos, but this is just a basic introduction to magnetism itself. We're going to start off with talking about the ferromagnetic elements in the domain theory. On the periodic table, there are three elements that are considered ferromagnetic. We'll talk about what that means in a second. And they are iron, with the symbol Fe, nickel, and cobalt. To be ferromagnetic means, what is, from an elemental standpoint, and our best understanding to this point with the domain theory, is that these are elements who can have their electrons spin in the same direction around the atom. As you will learn later in this unit, moving charges, such as moving electrons, create magnetic fields. So when the electrons all spin in the same direction, this causes a uniform magnetic field to take place throughout the substance, and therefore the substance becomes magnetic. You can combine various elements together into alloys. For example, a very common, very strong magnet is called an Electromagnet. And what you can, of course, see there is the three elements that are in that metal, aluminum, which is not magnetic, but probably put in that for strength, yet very light, and then nickel and cobalt, which of course are magnetic. All right, next thing we're going to talk about is how do you calculate the strength of a magnetic field. The symbol for that is V, and we're going to talk about magnitude and direction here at some point. If we had a rectangle which was 4 meters in length but 3 meters in width, and we have 12 lines of magnetic flux passing into the board. That's what the symbol X means. X is into the page or into the board in the Z direction. Really neat part of electromagnetism is that it's three-dimensional. So we have to come up with a symbol instead of left, right, up, down. We also have to have a symbol for into the plane of the page or board and out of the plane of the page or board. And then the symbol for into the plane is X, and the symbol for out of the plane is a dot. And sometimes you'll also see circle with an X inside it for into the page and circle with a dot inside it for out of the page. Nonetheless, we have 12 lines of magnetic flux passing into the page through this rectangle. So how do we calculate the strength of the magnetic field? The strength of the magnetic field, capital B, is the magnetic flux, which the symbol for which is phi, divided by area. So it makes sense to us that it would be the magnetic flux per unit area. Well, in our particular example here, we have 12 Webers, and there's your unit of flux, Webers, divided by, what do we have? 4 times 3 is 12 meters squared of area, and 12 divided by 12 is, of course, 1, and a Weber per meter squared is a Tesla. So this is how you calculate the strength of the magnetic field. The magnetic field is always stronger where the lines are closer together, and just like electric field, it is weaker when the lines of force are further apart. Okay? All right, let's talk about direction next. We're going to start off with a very simple, just a bar magnet here. We'll label the left end north and the right end south. And let's draw the magnetic field for a bar magnet. Magnetic field direction is defined to be the direction the north pole of a compass would point at that point in the field outside a magnet. So if we were to bring a compass near the north pole, the left side of this bar magnet, the north pole of a compass would point away from that. Like poles repel, opposite poles attract, the law of magnets. So at this particular moment right here, the magnetic field would be going away, and then of course it would be attracted over here to the south, away from the north, towards the south, outside a magnet. We'll draw a second line, away from the north, towards the south. Let's do some on the bottom here, away from the north, towards the south. Interesting connection here. Just like other fields we've talked about, these lines of magnetic flux can never cross each other. They can meet at a pole, but they can never cross each other. So make sure that you don't have your lines crossing over each other. All right, so that's the direction of the magnetic field outside a magnet. But if we were to, of course, follow through here and connect our lines, because magnetism doesn't just stop, then our magnetic field inside the magnet would be going away from the south towards the north. It has to complete the line of magnetic flux. So our rule of thumb here is direction the north pole of a compass would point outside a magnet, away from the north towards the south. Inside the magnet, away from the south towards the north. More on that later. Or to the right here, we have an interesting little diagram which represents the Earth. Well, we all know that we call the top of our Earth the North Pole, and we call the bottom of our Earth the South Pole. Why do we call the top of our Earth the North Pole? Because that's the direction the North Pole of a compass points. When we're out orienteering or using navigation, our North Pole North Pole of our compass points to the North Pole of the Earth. What we often don't do is we think about why is that? Well, the only reason the North Pole of a compass would point north is if it was attracted to a magnetic South Pole. And yep, that's right. What we call the North Pole of the Earth is actually magnetically south. What we call the South Pole of the Earth is actually magnetically north. And that has to be true, otherwise the North Pole of a compass would not point in that direction. The North Pole of a compass would not be attracted to a magnetic north. So really interesting little tidbit of information a lot of people don't realize. All right, we're going to finish up now talking about how do magnetic fields interact. And we're going to do this with a pair of bar magnets down here. Let's let the right end of this magnet be north, therefore this end would be south. And let's make this left end of this right magnet north, and its right end south. And how would we draw the magnetic field for this? Well, we have like poles. Like poles repel. So what would happen here is the lines would come away from the north and then get repelled away from the north towards the south. And then the same thing over here for the other magnet. And eventually, of course, these lines would come back around all the way over to a south pole. But we're just showing the interaction of the magnetic field between these two magnets themselves. Okay? You could do this for any magnetic field. I'm sure we'll be doing more of this as we do problems in class. All right, so this ends our introduction. And so this is the end of Electromagnetism Part 1.